This lesson is on the chain rule, which is a rule that we use for finding the derivative of composite functions. However, before we actually get into the chain rule, I'd like you to practice expanding and simplifying each polynomial first, and then find the derivative of that polynomial, because you already know how to do that based on our stuff with polynomial functions. Once you've done that, put the video on pause first, and then once you've done that, you can check your work to what I've done here on the video. Okay, for the very first one, I expanded and simplified and ended up with my standard form being what I have in this last line. And then I took the derivative. Now, I'm noticing that this will also factor, and we often want our derivative in its factored form so that we can solve for our critical numbers. So I'm noticing I could common factor a 3 out, and I'm left with this. Oops, that should be a 4 there. I'm left with this. Now I notice that this bracket is the same as this answer, which is the answer I got when I squared that binomial. So I'm just going to use that information from there and rewrite that as 3 times x minus 2 all to the exponent of 2. Hopefully that makes sense. Oops, undo. And then we can go on to the next one. All right, and when I expanded and simplified part B, I ended up with this answer right here. And then on this line, I've taken the derivative. And out of this, I can common factor a 36x, but then I'm going to look at this piece right here. This piece I've seen before when I squared the binomial here. So I'm going to rewrite that in its factored form. And of course, there's always method to my madness here. There's a reason why I'm doing this. Of course, the factored form helps us get the critical numbers, as I've already mentioned, but we're also going to look for some patterns, because we don't want to have to expand and simplify all of these polynomials, especially like, think of if that exponent here was a 10. That'd be crazy, or a different number, but it's still big. Or what if I made that a negative exponent or a fraction exponent? Then we're going to have like a different way of doing things. A negative exponent, we can use the quotient rule, but a fraction exponent, things kind of, well, we've done some of those as well, but the expanding and simplifying part doesn't work so well with that. So again, try the part C, put the video on pause, and we'll come back and talk about our findings. Okay, and for part C, I expanded and simplified and found that I came up with this line. And then I took the derivative, and I'm noticing the only thing I can common factor is a 2. But what I'm going to notice here, if I go back to my other two examples, I have something in the bracket right here, x minus 2, which appeared in the original question, x minus 2. And here I had a 6x squared minus 5, and you'll notice I have a 6x squared minus 5 here. And then the powers that are with those all are the older power reduced by 1. So I'm wondering if I could take what I have here and rewrite it as the product of what I have right here times something else. So let's see what we can come up with here. Let's see if we can use our skills from advanced functions and take that 2x squared plus 3x, so 2x squared plus 3x minus 1. Can we take that and long divide it into this 8x cubed plus 18x squared plus 5x minus 3 and see what we get as an answer if it actually goes in evenly. All right, so magically I've completed my long division here, and I do find that it goes evenly. So I can rewrite that 8x cubed plus 18x squared plus 5x minus 3 as the product of the divisor and the quotient, the answer we get when we divide. So now I'm going to zoom over here and rewrite this as 2 times 2x squared plus 3x minus 1, and it multiplies 4x plus 3. Okay, so this looks a little different than the other ones. Let's look for patterns here. So I'm going to go to the original question, the first original question, looking at part A here. So part A is this particular function, I know that when I had an exponent here before, to find the derivative, that exponent comes down front, and then I would reduce the power by 1. So if you notice our answer here, that exponent came down front, I have my base, and the power reduced by 1. That's amazing. Let's look and see if that works for this one, part B. So the exponent 3 is going to come down front. Oh, we have a 36, but I'm going to put another line in here. Let's put the 3 here for now. I would keep my base, and I'm going to reduce that base by a power of 1. Now, what I really had here instead was 36x. So let's take that 36x and divide it by 3. We're going to get a 12x here. I'm going to multiply by 12x. Now the question is, where does that 12x come from? Well, by golly, if you look inside this bracket here, if I took the derivative of what's inside the bracket, the derivative of the 6x squared would be the 12x. The derivative of minus 5 is just 0. That's interesting. Let's go back to part A. If I look at the derivative of what's inside of this one, the derivative of what's inside here would just be a 1, which is why we didn't need to worry about that for this question. Now let's look at part C. Overall, that 2 could come down front. There's the 2 right here. The base stays the base. The power reduces by 1. And then this should be the derivative of what's inside. So the derivative of 2x squared is the 4x. The derivative of positive 3x is plus 3. The derivative of minus 1 is nothing. Well, that's pretty cool. That's actually what our chain rule says. Our chain rule is when we have a composite function. So f at x in part C here, and in fact A and B as well, can be written as the composition of two smaller functions. And when we do that, we take the derivative of the outer function at the inner function times the derivative of the inner function. So that's where this is heading here. So a composite function is a function that's made up of two or more simpler functions. For example, I could have my function h at x. H at x is just given to be the composition of g at f at x, or of g of f of x. That's also written, or another notation for that, this does not say goff, or if you write it backwards, it doesn't say fog. This is just like an open circle, okay, g combined with f at x, or sometimes you don't even see the x and they'll just put g open circle f. All right, so for example, if I look at part B here, we had h at x being equal to bracket 6x squared minus 5 all cubed. Our inner function would be, or the f at x would be equal to the 6x squared minus 5, and my outer function would be this thing to the exponent of 3. So if we put that in just terms of x, it's going to be x cubed, x to the exponent of 3. So my h at x is equal to g at f at x. My iPad can't keep up with me, which means my g at x, that would be g at 6x squared minus 5. This reaches back into some 3u stuff that we did way back in the day. That's my f at x. So that means where I have x and g at x, I'm going to replace that x with the 6x squared minus 5. And that gets cubed. All right, so the chain rule is the rule used to determine the derivative of a composite function. So the chain rule says if h at x is the composite of two other functions, so we'll make that g at f at x, or g of f at x, then the derivative of h at x, then h prime at x, is going to equal the derivative of the outer function at the inner function times the derivative of the inner function. There we are. So we'll put that into practice, but we'll do that on the next video for this.